Very much. Thank you very much for the kind introduction. Good morning, everyone. I'm so glad to be in the University of Jaffna. This is a visit I have been looking forward to for many years, since before COVID. But because of the lot of issues, we had to postpone it several times. This visit to Sri Lanka and also to Jaffna. So finally, I'm glad that I managed to come here. And again, I thank everyone in the university, the faculty, especially the dean and the other staff who enabled this and supported my travel, hosted me to make this possible. So in this lecture, sponsored by IEEE Antennas and Propagation Society, I will give you a very overarching high-level overview of space-based opportunities and some associated challenges. You already heard about all these things, so I'll not spend any time on this slide. If you want to know more, it's very easy. Just take down my name and Google. You can find everything. And UTS, my university, has created the QR code also. That's directly linked to my profile page in UTS. So you can find a lot of information and some videos also in YouTube on related issues. Let's get back to the topic. The space is very interesting, not only scientifically and technologically, but also as a business. That's why a lot of companies are investing in it. The expected economy, the size of economy is $1 trillion by 2040 in this area. So the large companies like SpaceX in USA, OneWeb in Europe, and many other companies are spending, investing in this area. So coming back to technology and engineering and science, what can we do using space that we cannot do otherwise? Here are a few examples. Some telecommunications, earth imaging, sensing, etc. Position, navigation, and timing that we normally call GPS. Astronomy from space, scientific experiments, some space explorations. Starting from my favorite, telecommunications. Suppose you are in a place where you can't find internet, mobile broadband, like in a plane. How do you get internet? How do you get Wi-Fi? That's only through a satellite. The same if you are in a cruise ship or a navy ship in a remote area. The only way to connect with the rest of the world is through space, through satellites. In large countries, even developed countries like Australia, Canada, there are a lot of communities, remote communities, and some remote countries, for example, and areas like North Pole, there's no 5G or 4G or 3G or any G. There's no mobile broadband. The only connectivity path is through satellites. The same if you travel in one of these areas, in a vehicle, car, train, and so on. So to connect all these remote islands, remote communities, ships, yachts, planes, and those who are defending the country, defense troops, they need connectivity through satellites, through space. And the focus these days are in high throughput satellite communication. That means broadband or high data rate connectivity to all these people, to anyone, anywhere, anytime. Don't forget emergency services. In countries like Australia, for example, when I left Australia, we had floods in the north and bushfires in the west on the same day. That's the kind of emergency natural disasters we have. And to handle that, in these disasters, often we lose power. There's no power, it's blackout. And also because of the power loss, we lose the mobile base station, the signal. So it's a double blackout, no power, no communication. So to handle those situations for emergency services, in Australian emergency services, governments, volunteers need connectivity, high throughput connectivity that is only possible through satellites, and also to connect these families who are disconnected from the rest of the world due to these natural disasters. So that is the focus here. Most of current research and development is towards high throughput satellite communication. Also, there's another trend in low throughput satellite communication, that is to connect Internet of Things, IoT devices. These are very low data rate, things like sensors on a farm that can monitor moisture level, for example, and through networks like the one developed by a company called Fleet Space in Adelaide, Australia, you can monitor the status of your farm from anywhere you are in, through cloud, through internet. So that is not high throughput, so low throughput, low data rate, but they want to make this very, very low cost. So this is another research and development area. Other than that, there are many established space technologies, satellite technologies. For example, satellite TV existed for a long time. That's very low cost. And also low throughput satellite communications like satellite phones that has been around for a long time for voice and low data rate, that is established. There's very little research and development happening in those established areas. However, there's a modern trend, modern development from normal phones, like on iPhones. If you happen to be in a remote area with no signal and you get lost, what you do from the phone is it will be possible to send save our souls like emergency message containing your location, your GPS location, to rescue services. So it's a very, very low data rate. Only thing you send is your location and few other metadata, few other tags. So this is being implemented in iPhones, and hopefully that will be available in other smartphones as well. And that comes through satellites. So there are a lot of telecommunication options through space. Some are already established, like satellite TV and some other satellite services, and a lot happening in other modern areas. Sensing from space. For example, Earth observation. We were in USA last year in their summer around July, and very hot, dry area around Portland and Washington State. And we wanted to go for a drive through the beautiful countryside, and always we were concerned about bushfires. So what I just Googled to find where the bushfires are, and I got a map. And it turned out that that map is automatically generated by the data collected by satellites, Earth observation, remote sensing satellites. So without any manual intervention, without anyone, the satellite can observe this area, I mean, pretty much entire USA, and find the hot areas and update the map. That doesn't guarantee that there's a bushfire, but that gives a warning, so you can find the potentially dangerous areas and avoid them. And that's an example of Earth observation. Very, very automated, low cost once you launch the satellites. In fact, Australia had plans to launch 4 additional satellites like that. This is a kind of artistic impression of type of satellites NASA has launched for Earth observation. There are many, many other satellites too. Another Earth observation application is ship detection. Ships are supposed to transmit a beacon to identify them. If they don't, that's most likely they are doing some illegal activity, and you can find them. You can catch them from satellites through observation, and that applies to to stopping people smuggling and other national defense activities. So how do you do that? All done by radio frequency radars, like synthetic aperture radars, SARs, sometimes with some help with optics, because the radars can see through rain, they can see through clouds, they can see in the night. So that is how we do that. We have some projects in these areas related to sensing from space. Another application is position, navigation, and timing. And I'm sure all of you have used this. We don't call it in day-to-day life, we don't call it PNT, we just call it GPS, right? But GPS is a type of satellite system. It's actually an example of GNSS, Global Navigation Satellite Systems. So GPS is the first system developed by USA, initially for military use. Now they have released most of the signals for public use. The other countries have launched their own systems like Europe, China, etc. The theory is, if you this is your location, you want to find your GPS location or the location on Earth. If you can see at least 3 satellites, you can work out from their signals the distance from each satellite to you. So in 3D, if you can see 3 satellites, you can locate, you can find your location. And if you can see more satellites, you can do this more accurately. So what's new in this area is the use of multiple frequency band, like multiple bands in GPS system. If you have an even better receiver that can get signals from these multiple systems like American system, European system, etc., it will work better, even better accuracy. And then some other areas like passive radar to use GPS signals to locate, identify objects. That's a very new area of research. Other space-based opportunities like astronomy. Space is a fantastic place to do optical astronomy because there's no rain, there are no clouds. So if you have a telescope in space, you can explore the space, galaxies and everything, pretty much 24 hours, 7 days per week, free of all these secondary effects, weather effects, etc. This image is from the James Webb Space Telescope. That's a massive space observatory telescope controlled by NASA. And you can go to their website, you can see amazing pictures they have captured from this telescope. You can do various scientific experiments in space in places like International Space Station, and of course, space exploration, missions to other planets, etc., has been happening, not only now, many years ago. One example is some 50 years ago, when Neil Armstrong set the foot on the moon. So you may have seen the videos of Neil Armstrong coming out of the lunar module, who's stepping down the ladder and stepping on the surface of the moon. If you Google, you can still find some of these videos. And these video clips are telecasted around the world in real time, from moon to your TV set. How did we get that signal? We got this signal through this dish in Australia. This is a massive radio telescope dish antenna, reflector dish antenna, in Parkes, 64-meter diameter Parkes radio telescope in New South Wales, not too far from Sydney. And in fact, they used another one, 24-meter diameter dish in Honeysuckle Creek, close to Canberra, that was controlled by NASA those days. So they kept these two to get the signal. Parkes was a backup. This was the main dish. But it turned out that because of the timing and the larger size of this, the signal was much better. Signal to Parkes was much better. So most of the transmission, the live streaming from moon came through this dish. So it's like 50 years ago. So several Australians, including myself, those are all past chairs of IEEE New South Wales, formed a committee and submitted a case to IEEE proposing this to be declared as an IEEE milestone. IEEE milestones are national historic benchmarks or milestones happen in engineering related, technology related areas. And this was accepted by IEEE headquarters and history committee, and it became the first IEEE milestone in Australia. So this photo was taken at that event. IEEE president and few others, IEEE leaders in this site controlled by CSIRO. And this is IEEE plaque. If you go to parks, you can see this IEEE plaque, the milestone plaque in that location. So that's going back a little bit about this exploration, but these things will continue to happen to inspire young researchers, students, etc., about the challenges and exciting space. So I mentioned satellites several times. What is in a satellite? It has solar panels because that's how they get power. They have lots of antennas for various purposes. Some of the antennas are dishes like this one, dish antennas, very easy to recognize. Some other antennas are not very obvious, some flat panels. Then there's a lot of electronic stuff. We normally call it a payload. So if it is an image Earth observation satellite, the synthetic aperture radar is the payload. And obviously there are many mechanical propulsion system, etc., that I don't know anything about. This is this picture from NASA indicates the solar panels and the other parts in typical satellite. And talking about the sizes of the satellites, so conventional satellites are large. They are the most expensive and to make and to launch. Then there are smaller satellites called nanosatellites. The smaller satellites are CubeSats. They are the smallest and cheapest to make and launch, mostly because they have standardized sizes, 1U, 3U, etc. So you can pack several of those things into one rocket and launch at the same time in the same trip. So to give you an example, this is the launch. This is the rocket, the Falcon 9 rocket launched by SpaceX in December 2018, and it carried some more than 50 satellites and launched all of them and came back. So that's the kind of launching capability, state of the art. One of the satellites in that rocket was this. This is the expanded view of the Odyssey 1 CubeSat. And this happened to be the world's first entirely Ka-band CubeSat made by an American company called Odyssey Space. That's a spin-off from Stanford University in the USA. People consider Stanford as one of the top engineering universities in USA together with MIT. So the graduates from Stanford created this company. It's a spin-off in Silicon Valley in USA. I gave IEEE Distinguished Lecture in Silicon Valley in 2017. That's my first year as a Distinguished Lecturer of International Propagation Society. I gave about 25 lectures that year. This happened to be one of them, one of the three in USA. So it was focused on industry especially, and several companies attended that. Reps from, it was held in Texas Instruments, I think, on Semiconductor Drive. And some came from Odyssey, so young engineers, and they asked me to design the antenna array, high gain antenna array for their satellite. So we did. You can see, you don't, probably hard to see here, that is, it's actually two arrays, two flat phased arrays that we designed for this landmark satellite. So we designed that, they fabricated it in USA and measured the performance, and we evaluated it. It was pretty good, so they integrated that into the satellite and launched with the satellite. So that made this the first Australian design antenna system launched to space in almost 2 decades, since our Australia's own FedSat launched in 2002. That was the interesting part of the project, but the sad part is the mission failed after the launch. The satellite was lost, and the Odyssey one, actually the company sold their assets. I believe they are now owned by an Australian company called US Systems. So hopefully that technology and the other innovations they wanted to introduce, including a space network connecting CubeSats with your computers continuously, that probably come back in the future. So coming back to satellite communication again, talking about satellites, there are three ways. There's another way to classify these satellites based on their orbit. One is some are geostationary satellites, geosatellites. They are in the geostationary orbit, also known as Clarke orbit, named after Sir Arthur C. Clarke, the former chancellor of Moratua University, because he worked out and published this possibility that with 3 satellites in this orbit, you can cover the whole world communication. And there are few other advantages of keeping the satellite in this particular orbit by balancing the centrifugal force, etc. So this orbit is 36,000 kilometers above us, very far, and all these satellites rotate at the same speed the Earth spins. That makes the communication relatively easy, because if you relative to us, all the satellites are stationary. So when we point the antenna, like the satellite TV antenna dish in our house, we need to point the beam very accurately towards the satellite. Once this is done, it's done. Then you don't have to worry about it. It's always point to the same satellite. The beams of some of these dishes, especially for high throughput communication, could be very narrow. The beam width is in the order of 2-3 degrees. And so you need to align very accurately towards the satellite. But because of the geostationary nature, once it is done, then it's very easy to communicate. The other satellites, like medium Earth orbit satellites that are at lower orbits, these are modern satellites, and MEOs are less popular. Low Earth orbit satellites are also a modern new generation, sometimes called new space. They are the most popular. Very good examples for low Earth orbits satellites are the Starlink constellation, that's at 400 kilometer orbit, and the OneWeb constellation is at 1,200 kilometer orbit. Those satellites are not geostationary. That means relative to us, the satellite moves in the sky. And so when we have an antenna or the terminal with a pencil beam antenna, we need to track the satellite because the satellite moves in sky. And very accurately, we have to follow the satellite path. So the way to, I will just show one more slide about geostationary, and then go to low Earth orbit LEO. So this is the Clarke arc, or the orbit, or the geo arc. The satellites, this diagram was generated in 2011 by Boeing. You can see it's almost 300 satellites in this orbit. at that time, and 70 of them were Boeing, and all the other major satellite operators like Intelsat, Inmarsat got their satellites in this orbit. Optus is an Australian telco, and almost all satellites broadcast in TV satellite signals are in this orbit. So it's pretty much full. There's not much you can do in this orbit. But the other orbits are not full. This is OneWeb constellation. This is relative to Earth. You can see all these dots are satellites. They move relative to us, relative to Earth. So when you try to communicate, this is your user terminal. This is the satellite. The satellite goes above you and moves above you. Some of the satellites have several beams, and the beam changes with time. And after a while, that could be like 2-3 minutes, the satellite disappears. See, this user terminal can see the satellite, different beams coming from the satellite, and this is the last beam, now it's gone. So what do you do now? You got to catch the next satellite. So when you have the satellite, you have to very accurately, very precisely point your 2-degree, 3-degree beam with beam towards the satellite. And then once it's gone, you got to catch the next satellite very quickly. OneWeb has about 650 satellites in the orbit right now at 1,200 kilometers. Now, the other constellation, the largest one, Starlink, this is the Starlink satellites in this region. You can see Sri Lanka here. This is a snapshot I generated when I was in Colombo a couple of weeks ago. But if you go to this site, actually, you can get a real-time map. It shows how the satellites above you and how they are moving. You can put in your GPS location, and in real time, you can see that there are lots of satellites, 400 kilometers above us, about 5,500 in orbit now, about 12,000 planned, and some say that eventually they may have more than 40,000 satellites. They're all low Earth orbit, non-geostationary satellites. So imagine there are going to be a lot of satellites in space. Already there are quite lots of satellites. So this is the OneWeb constellation. Again, a snapshot, fewer number of satellites, as I said before, 650 or so on a different orbit in this region, again, around Sri Lanka. But always is one satellite that is visible to any location. That's the idea. So always you have communication through one satellite at least, sometimes more. GPS satellites, they are also low Earth orbit. There are quite a few in this area at that time, at the snapshot. Okay, a little bit about satellite communication. What you need to communicate when you are in a remote location. Suppose this is your user terminal. You are in a remote area. So you don't have a signal. Your smartphone doesn't work. There's no mobile broadband signal. But still you want to update your Instagram or Facebook. So your only way to connect with the rest of the world is through a satellite. So that's your beam, uplink and downlink, communication link with the satellite. And then the satellite got to be connected with internet, right? So there's another path, another connection from the satellite to these so-called ground stations or gateway stations. And the gateway station is permanently connected with internet, normally through a fiber optic link. So your data goes to the satellite and comes back. This is called the so-called bend pipe configuration. The frequency and other things can change, but more or less going up and coming down, and then vice versa in the other path. But in some situations, this satellite may not see a ground station. In that case, there are links between satellites called inter-satellite links. These links could be optical or radio frequency, but this is a very new area of research we are conducting research in this area as well. Communication links between satellites, radio frequency communication links. So then your communication goes to one satellite and then through the link to another satellite, maybe a few more other satellites, and then come down to a Earth station and to internet. Okay, so that's basically the network. It has a space segment. Those are basically the satellites and the inter-satellite links. And then on the ground, you have the user terminals and the gateway station. So quite a bit of research and development happening in all these areas to address those challenges. To understand the second part of the link, so you already seen the terminal, user terminal, and the beam to the satellite, the white beam. And you look carefully, so that is the white beam from user terminal satellite. This red beam is from the satellite to a gateway station. That red dot here is a gateway station. So that's the second beam from the satellite. So together, these two beams or these two links form the SATCOM, the main part of the SATCOM networks. Again, the gateway this is the red link, the gateway to the satellite, and this is the white link from the satellite to the user. That example is from OneWeb. So a lot of challenges are associated with this space segment. I will quickly, I think I will skip these things because there's quite a bit of technical material as well, given that we are running out of time soon. So in the space segment, we want to make the satellites systems, reduce the power consumption, make them lighter, increase the data rate, that means increase in the bandwidth, etc., reduce the cost, and make better inter-satellite links. In the gateway stations, they are fairly expensive, very large dishes. Again, to reduce the cost, the real estate is a problem here, expensive in a lot of countries, increase in the bandwidth to increase data rate, possibly create multiple beams to see multiple satellites from the same gateway station, etc. User terminals, this is a lot of challenges here to reduce the cost, have wide bandwidth to get large data rates, need high gain pencil beam antennas. Even if your terminal is stationary, to communicate with LEO satellites or MEO satellites, your beam has to steer and follow the satellites. And sometimes you need low profile antennas, flat panel antennas. If you are communicating while we are moving, you can stop and communicate. That's called communication on the pause. And sometimes you want to communicate continuously while you are moving, like you're in the car. So a lot of challenges associated with these different modes of users. Going a little bit back into history and statements, the Starlink owner Elon Musk said his main challenge is not launching thousands of satellites. That he did already, rather developing a user terminal antenna for Starlink. So this is the first product, user terminal product from Starlink. There's another newer one in the market now. There's another story from Panasonic Avionics, and that is another highlights the difficulty in first product they made. In fact, the Boeing USA made for them electronically stable antenna costed $1 million each to fabricate, to manufacture. To highlight the challenges, but the world changed. The R&D made breakthroughs, and there are some products at the moment. This is a large market, the flat panel antenna. It's expected to be about $2.5 billion by 2030. So a lot of companies are investing in this area. Some of the products are here, commercial products. This is a dish antenna with heavy-duty motors and so on, specially made for Navy ships. This is made by a company called EM Solutions in Australia, and these have exceptional performance, fantastic antenna systems, but they are very expensive. So in operation, these are normally covered by a radome, dome like this. You can see similar things in Navy ships, cruise ships, even for satellite TV, in on military vehicles. Can see some of these. The dish antenna is another product like that. Intellian, there's a dish antenna and the dome around it. This is a two-dome setup from Intellian. Two dishes, one dish in each dome for low Earth orbit satellites. This is especially for the OneWeb network. So one dish is following one satellite, the other dish is waiting to catch the next satellite. Then when you lose the connection here, then this one starts communicating with another satellite. So another type of antenna system, this is a flat panel dish. This can be tilted around and rotated to communicate with satellites. These are used in airplanes. These are made by several companies, American, German, etc., Chinese. And if you see a little hump on the top of an airplane, most likely that's because they have fitted one of these antennas on the top, retrofitted to get Wi-Fi to the plane, to communicate with satellites when they are flying. Then there are a few methods developed by academics and other organizations that to steer the beam without tilting. This is one developed by Communication Research Center in Canada about 10 years ago. It's quite tall, but it does not require tilting. And this is another product primarily developed in Portugal. It's still being developed that does not require tilting either. This needs some translation of this top plate. Previous one needs rotation of these plates to steer the beam. And then there's some electronic versions of that. This is also not very thin. The horn antenna here and electronically controlled surface here to steer the beam electronically. Talking about electronically steered antennas, there's some here. Some examples, Chimera is probably the most successful. Some say they raised some 700 million US dollars or something like that to develop this product, but they are successful. They have commercial product now. Some other companies changed their ownership to others like Phaser and Alcon, I believe. This is the British company. The Alcon German company is still working in this area. So you can find few papers published by Chimera about their technology. I will go straight to one of their products. This is one of their antenna systems fitted onto the roof of a vehicle. So this is electronic, and you can communicate with satellites while you are moving. So that the satellites on the move or communication on the move. They are still fairly expensive. These are some figures I found in. You can purchase these things in several countries, including the US. And these are some example prices upfront and the subscription. So it's still fairly expensive. Another non-tilting antenna system comes from another American company called Thincom. This is one of their products, newer products. This is known to be very good and very expensive as well, specially designed for aeroplanes. So this is thinner, so better than some of those that are taller. Based on method called VICTS, Variable Inclination CTS, that is based on a old Raytheon patent, few patents and so on. Now in 2017, with a PhD student, I invented an entirely different method to steer the beam of antennas and created the flat panel thin antenna system using rotatable meta surfaces. And now sometimes this is also called near field meta steering. Go to the next slide. And this is our paper, the first paper about this method that we published in IEEE Transactions on Antennas and Propagation. So in this method, you can use a base antenna, normal antenna with fixed beam. It can be any antenna pretty much. It doesn't have to be planar and high gain. It could be non-planar. Excuse me. With medium gain, it works better with planar antennas. And works with high gain antennas as well. So that has a fixed beam. And then we add 2 additional discs, the disc 1 and disc 2. These are specially engineered metasurface discs, usually metasurface discs. And we rotate these thin metasurface discs independently using low-cost motors. So it's a mechatronic mechanical method, but there's no tilting of any parts. By doing so, we can steer the beam of the antenna in both planes, and we have demonstrated steering in within a large conical volume with 102-degree apex angle. That's plus or minus 51 degree from the vertical, and any direction in the horizontal plane. So how does these systems operate? Look at these 2 discs. Here we are rotating both discs in the same direction. And when you do that, the beam goes, beam angle changes on the horizontal plane. We call this azimuth angle, a change in the azimuth angle. The second one, so that's the co-rotation. This is counter-rotation. Follow these lines, and you can see that the 2 discs are rotated in opposite direction. When you do that, the antenna beam goes up and down. So we are changing the elevation angle of the beam. The horizontal angle does not change. So by combining these 2 motions, a linear combination, we can steer the beam from any direction to any direction within that large cone. So that's how it's done using stepper motors or other rotation means. So this method has many advantages. I will not go into the details considering the time. We developed this from medium gain antennas to high gain antennas. We developed many different types of metasurfaces. These are printed circuit board type metasurfaces with dielectric and metal patches on dielectric slabs. Also, we developed metal only metasurfaces and some dielectric only metasurfaces. These were done with the Australian Department of Defense. Our defense collaborators, Girl and Borg, we published together jointly these results that were declassified by the Australian Department of Defense. And you can find this information in our papers. So our Eureka Prize for outstanding science in safeguarding Australia, that was partly due to this work we have done with Department of Defense. So that's why we call our team Meta Steerers team. And this is one of our products. So we develop fixed antennas with fixed beams, circular polarized antennas with very high gains as the base antenna, and then use this method to steer the beam. The method, and this is a rotation system developed by Australian Department of Defense for this particular project. So this method became very popular around the world. Very prominent research teams in other countries in USA, Canada, Europe, China, India, etc. are using this method to steer antenna beams. This is one example presented by Professor Yaya Ramsami's group in University of California, Los Angeles, UCLA, well known for their space-related research, some antennas they made for NASA, etc. So they applied this method to steer the beam of the antenna. One antenna design is this paper. And the other people applied for entirely different applications. This is for near field scanning at even higher frequencies, up to terahertz, using the same method by rotating metasurface-like structures. So a lot of things happen in this area since we invented this method and first published this method, that is placing metasurface in the near field of a fixed beam antenna. But what's most pleasing is its impact on industry, in companies, in real life application. The defense company, it's a defense giant in France called Thales, published this paper in 2022 European Microwave Conference. This is their prototype, antenna prototype, and they also used the same method. They created these metasurfaces. They call this deflector using a 3D printing method they developed. So it's a dielectric only metasurface doing the same thing. Basically, each of these metasurfaces or discs behave like a prism, optical prism, but electrically it doesn't look like a prism. It's a flat disc, but it's electromagnetically it behaves like a prism. For that reason, this method is also called Riesler prism method. So another company, Airbus in France, the same company that makes Airbus planes, they do have a division for space related systems, including satellite communication. They also shown in 2023 European Conference on Anti-Propagation booth a terminal they are developing. Another company is in Italy called Veva. They applied the same method to steer the beam of this antenna. That's the antenna with the fixed beam. It's a metasurface antenna with a fixed beam, and they added, two other metasurfaces. They call them meta lenses, but the same thing, and rotated them to steer the beam. So a lot of applications in industry and also in governments. This is a defense university in China applied this method to steer the beam of a high power microwave beam using this method by developing all metal metasurfaces and all metal horn. And my group done a lot, and you can find all that in our papers, the all metal metasurface structures and so on. We published recently. From fifth year engineering project students to the PhDs and postdoctoral fellows in my team to conduct research in this area, various aspects. This is a current project we are doing, $1.1 million project funded by the Chief Scientist and Engineer Office of the New South Wales Government. And in this project, we are trying to build a user terminal for OneWeb network. And we expect that that's the world's only SATCOM user terminal that can operate entirely on renewable energy. This is very important to handle natural disaster situations like bushfires and floods in Australia. In fact, during our project, we reached a milestone very recently, about a month or so ago. We were able to receive transmissions from OneWeb satellites that are flying over our university, over Sydney. So as I said before, they move above us, and our narrow beams antenna system was able to track the satellite and continuously receive signals from these satellites, which we can't see from Earth, but we can see the signal when we are receiving it. That made our antenna the first ever Australian-made terminal to receive transmission from commercial LEO communication satellites. So we are going ahead with that project. At this point, I want to say a few things about our research. We only try to conduct good research and publish in good papers in good journals. And our PhD students publish top-class thesis. And they are often ranked in the top 5 to 10% in the world by international experts. So the papers in IEEE journals like Transactions and other IEEE journals, that's all we do. We have published quite a lot of papers, and all the other things, the citations, the awards, and all these things are sort of byproducts of this good research. The secondary results, H-index, you heard, the Google citations, world ranking in Google Scholar, number 2 in antenna engineering in the world, number 2 in the world in electromagnetic engineering, and so on. A lot of those things happen, but they are all, as I said before, they are secondary and they are byproducts. Especially about awards, we were quite successful in the last, sorry, I had to go back. The last 24 months or so, quite successfully, got 10 or 11 awards, and 8 of them were national or state awards, including those you heard, the Eureka Prize 2023 for Outstanding Science in Safeguarding Australia. Year before, in 2022, Professional Engineer of the Year. That these two together, sitting side by side, is unique because no one received both of them, a Eureka Prize and the Professional Engineer of the Year award before this, because this is for outstanding science, this is for outstanding engineering, and half of our work is engineering, other half is science. The other other unique combinations are this Defense and Space Awards. These are 2022 Australian Space Awards, Excellence Award, etc. And this is 2021 Australian Defense Industry Awards, Excellent Award, etc. So again, getting both of these is a unique combination. The others, Chancellor's Medal Research of the Year 2023, Chancellor's Medal 2022, and so on. Now, this being a IEEE sponsored event, these are all IEEE awards, including one for the most cited paper in IEEE Transactions on electromagnetic compatibility. And these are Engineers Australia awards, and few here are actually from Institution of Engineers Sri Lanka, New South Wales chapter. And I could not put in the other awards here, ran out of space. Same here, I ran out of space. These are some of the collaborators we collaborated with. Can see many companies in Australia and overseas. These are Australian companies, these are overseas companies, a lot of research organizations like CSIRO in Australia and CRC, etc. in other countries, SciMeta and so on in UK, many universities throughout the world, in Australia, overseas, many in North America and Europe, a lot of European universities. So we have done a lot of joint research, published a lot of joint papers. About my university, I will not spend a lot of time, maybe 2-3 minutes. This is our building, UTS Engineering and IT building, and my office is somewhere here. And this is Broadway, one of the busiest streets in Australia. And this is the most exciting photo about UTS. And so it's a wonderful place. So this is Sydney Opera House. This is Harbour Bridge. This is Circular Quay ferry terminal. So international cruise terminal. Harbour, Darling Harbour is on this side, and Hyde Park is on this side. And this is Sydney Central Business District. And our university is in the middle of that, and very close to, very short walk from the central station. So beautiful place to study and relax. If you want to, you can just walk into any of these very popular locations and very quiet locations when you're studying. About ratings, I mean, you can't talk about a university without talking about ratings these days. I will only highlight the ARW ratings of specific areas. Our university in computer science and engineering is number one in Australia, 17th in the world. In electrical and electronic engineering, number one in Australia, 27th in the world. In telecommunications engineering, we were number one in Australia. We are now second. Hopefully, we will come back to first position again and number 11 in the world. So it's very significant in Australia and globally in research and development in this area and also teaching. The other figures, I will skip that, except that we have a collection of very interesting, sometimes weird buildings. This is my favorite building, this building 2. There's a lot of glass, and this is our rooftop garden, and that's where we conduct our experiments, satellite experiments, getting transmissions, receiving transmission from OneWeb satellites. So another few minutes about IEEE, because my travel was sponsored by IEEE. It has a lot of societies, and IEEE is a name, not an acronym anymore. It's not limited to electronic engineering. Now there are a lot of non-engineers who are members of IEEE as well. It covers pretty much all areas of engineering, electrical, and technology. A large number of computer scientists, IT professionals are members of IEEE, and we cover all these areas. Then skipping a few slides, let's get to the Antennas and Propagation Society. And this is our Society of Antennas and Propagation. Again, we have very diverse areas of interest, not just antennas and propagation. It's not a very large society, relatively. We got some 10,000 members, but we are growing, and especially growing in Asia Pacific. Region 10 is Asia Pacific, from Bangladesh all the way to Japan, New Zealand, and so on. And see the numbers now. Most of them, the largest largest region is Asia Pacific, and it's growing. And the society is funding very healthy financially and funding activities in these areas, in these regions, especially in developing countries, in Asia, in Africa, and South America. We want to increase our student numbers and young professional numbers. So we welcome students to join, and the society funds a lot of projects in this area, activities in this area. For you to access funds from the society is very easy, especially if you are in the developing countries. So the way we fund is through chapters. Our chapter numbers are also growing. Again, in Asia Pacific, a lot of activity is in India, new chapters coming up. The chapters are sometimes under section, and some of the chapters are actually under student branches. For example, we have in Jaffna University as IEEE student branch, you can create antennas and propagation chapter under your student branch, and you can decide what you want to do, the activities you can do. For example, the activities are the general activities, the funding for baseline activities like $500 per year that you can use when you need minimum two events for that, and submit the annual report. If you are doing more things like workshops, for example, this event could be a workshop, and for those events you can request more funding through special project funding, and they are very happy to support that events. For example, if you want to bring some international visitor come into university in Colombo, and you can encourage them to come to Jaffna and provide travel, accommodation here, and support like that. So sort of support universities don't have spare funding for these days. As you know, in Sri Lanka and also other countries, there are a lot of students who like to do professional activities like this. This will allow you to develop your leadership skills. That's why all my students started as IEEE leaders, student leaders, by creating chapters. I formed the student branch chapter in Macquarie University, in student branch, and also the student branch chapters. And my students had the opportunity to provide their leadership, work with the team, demonstrate their capability, and that helped them to get good jobs when there's a competition for jobs, good academic positions when there's a competition for academic positions. That elevated their profile for their IEEE voluntary work, uh, for their teamwork, for their leadership, and several of them became IEEE leaders. In Australia, the current chair of the IEEE New South Wales section is one of my students, mentees, and previous secretary, and so on. Some of them are Asia Pacific region leaders, and some of them are world leaders. So that's a very good time to think about you if you're a student or a early career researcher, to start your leadership skills. And you don't need to burden the university and other organizations about funding when you try to organize. You can invite people from industry, people from other universities, and even some international visitors. Sometimes the society funds directly to travel to your university, but sometimes you need a little bit of extra that you can use for accommodation, for provide create a workshop and invite people and provide everybody snacks or meals and things like that for all interactive activities. They don't have to be about antennas or propagation. Anything related to wireless, as I mentioned you earlier, anything related to wireless, sensors, communication related things, and software related things, they are all workshops and activities and competitions. All these are supported as special projects. All you have to do is organize yourself and ask for money at the right time through these chapters. So what is the cost to you? If you are already IEEE student member, to become a AP Society, at AP Society student membership, just $1 per year. That's not much. That's from this year, which we reduced. Actually, it was more. And if you have a couple of champions and about 12 student members, then you can sign a petition and create your chapter. And from there on, you can request funding. So as I said before, the baseline, $500 per year for each chapter, and then for each additional activity, workshops, special projects, competitions, and all this, you can ask extra funding every year. So think about this your professional career, professional engagement. That helps, that will decorate your CV, your resume, in addition to all your good marks and transcripts and all that papers, research achievements. This is an additional thing that can highlight your capability, especially in leadership, in teamwork, and in other skills. Normally, people would like you to have in large range of professions. So with that note, I think you're already gone over 1 hour. So there are a lot of other things you can apply for scholarship, travel grants, etc. You can find that information in internet. I think I gave you a brief overview. If you need more information, send me an email. I will connect you with the right people in the society. And I know those in your student branch and the Sri Lanka section as well. I gave the keynote speech in the IEEE Sri Lanka annual general meeting a week or two ago in Colombo, and I met several IEEE leaders in Sri Lanka and students who are very interested in doing more activities and get extra funding from overseas to do that. And that's quite useful for countries like Sri Lanka and all developing countries that has limited resources, financial resources, but lot of bright students and interested in doing just more than just more than passing exams, right? To show your capability and your skills beyond the basic that we all expect you to have when you graduate. This is all extra work, voluntary work that will decorate and highlight your capabilities in your CV. So to end this presentation, let me go back to space. So I started from space offers massive opportunities for the advancement of humanity and improvement of quality of life. Think about people who are living in remote islands, even in Australia in some parts with very poor internet, mobile broadband, and with this technology. Those are the issues we're trying to address: the digital divide across communities, and also emergency services when they are in trouble, when handling natural disasters, how to provide better support to affected people and to keep people connected during emergencies. So nearly all these modern space-related technologies require advanced radio frequency systems, including sophisticated antenna systems. That's why that's my favorite area. But your favorite area may be in that as well. A lot of digital electronics, a lot of signal processing. All these antenna systems are software controlled. So all of them go to software system, control system, some firmware to control mechatronics, etc. Quite a bit of mechanical parts, and so on. So it covers a lot of areas in IEEE and also beyond IEEE. A lot of opportunities because there are many challenges that have not been solved. People are trying to find solutions. Companies, universities, research organizations, governments still trying to find solutions. So significant research and development challenges remain in these space-related technologies, even within our discipline of electronic and telecommunication engineering, electrical, including, and also other disciplines in software engineering, IT, software engineering, IT, and so on. With that note, I will end my presentation, and I'm happy to answer any questions from the audience. Thank you.